A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Today we will be discussing the engineering thermodynamics, and at the end of the lecture we will also discuss the statistical mechanics. Statistical mechanics is not actually the part of our course, but we have mentioned a very brief review of the statistical mechanics just for basic understanding and just for comparison with the classical thermodynamics. So the basic engineering thermodynamics and statistical mechanics are the themes of this lecture. For starting the lecture, we need to know the microscopic and macroscopic approach of any particular systems. We have microscopic viewpoint of any particular system and macroscopic viewpoint of any particular system. And generally, the thermodynamics is considered to be the macroscopic viewpoint of any particular system, and statistical mechanics describe the microscopic viewpoint of any particular system. So in microscopic viewpoint, on the basis of statistical consideration and probability theory, we deal with the average values of all atoms or molecules, and in connection with the model of that of the atom. So that is actually the statistical approach, and that is called as a microscopic approach as well. We have macroscopic approach, or that is also called as macroscopic point of view, and consider the gross, or in this particular case we need to consider the gross or average behavior of a number of molecules that can be handled based on the continuum assumption. In this case we are actually interested in the measurable property instead of just like the temperature, pressure or volume, but we are not actually interested in the microscopic behaviors of the particle involved in contributing to that property. So we mainly deal with the time average influence of many molecules. This macroscopic or average effect can be perceived by our sense and measured by instruments, and this leads to our treatment of substance as an infinitely divisible substance or continuum. So again we are describing the nomenclature of the thermodynamics, that is the system, surrounding and boundaries, and we have closed systems. Systems is the anything of the under consideration, and surrounding is the boundary in between the system and anything that is not under consideration, and boundary is actually the region or space in between the system and surrounding. We have closed system or open system depending on any particular configurations. So an open system's mass and energy can transfer between the systems and surrounding, while in closed systems only energy can transfer. While in case of isolated systems, nor mass nor energy can transfer the boundary. So we have some of the properties of the system already discussed. This might be intensive and extensive property. Depending when the property depends on the mass of a system, it is called as a extensive property, and if the properties are independent of the mass of the system, such as temperature, pressure and density, it is considered to be intensive property. And the example of extensive properties include the mass and volume of any particular system. And from that we can move toward the specific properties. We have some of the configuration of the system, just like we have equilibrium configuration, which is actually the state of balance. In equilibrium state there is no unbalanced potential or driving forces within the system. We have thermal equilibrium, mechanical equilibrium, phase equilibrium and chemical equilibrium. In case of thermal equilibrium, the temperature is same throughout the entire system, while in the case of mechanical equilibrium, if there is no change in the pressure at any point of the system with time, so we consider the system to be in mechanical equilibrium. Phase equilibrium actually describes that if a system involves two phases, and when the masses of each phase reaches an equilibrium level and stay there, so we say that this system is in phase equilibrium. And in case of chemical equilibrium, we can say that the composition of the system does not change with time, that is, no chemical reactions is taking place. So just like in this case, we have a type of this system is not in thermal equilibrium, because initially the temperature at different point is different. Here we have 20, 23, 30, 35, 40 and 42. and this is actually the part of the system. But after some time there is gradual heat transfer from the region of high temperature toward the region of lower temperature, and this continue until all the places or all the points in the system achieve the same temperature. So we are looking toward the next case. After achieving the thermal equilibrium, we see every point in the system have the same temperature, just like 32 degrees centigrade is achieved everywhere. We have some processes or cyclics, which is called as a process or path. So a process is actually any change that a system undergoes from one equilibrium state to another. So path is actually the series of states through which a system passes during a process. So if we describe a process completely, one should specify the initial and final states as well as the path it follows and the interaction with the surrounding as well. We have some quasi-static and quasi-equilibrium process or quasi-equilibrium processes, and when a process proceeds in such a manner that the system remains infinitesimally close to an equilibrium configuration, so this is called as a quasi-static. So this is a type of quasi-static or quasi-equilibrium processes where we have slow or quasi-equilibrium processes are very fast, that is actually non-equilibrium processes. So the system can undergo from one state into another state, and the process is a type of quasi-static and non-quasi-static respectively. So we have the phase diagram plotted by employing thermodynamic property as coordinate of very useful in visualizing the process. This is actually called as Pvt diagram. Here two thermodynamic variables are plotted, that is the pressure and volume. So this is only PV diagram, but we can also express this in terms of three thermodynamic variables, that is called as Pvt diagram. So some common properties that are used in coordinates are temperatures and pressures as a coordinate and volume. So if we have some different processes that are described, just like isothermal process, isobaric process, isochoric process, or cyclic process. The iso actually defined that the temperature in isothermal temperature is constant, volume is constant in isochoric process, and pressure is constant in isobaric processes. Here we have some example of the quasi-static process where we can move the system so slowly that the it is assumed that the change in the property of the system is almost negligibly small. So just like if here in this case we are bringing the system from this point A to point 2, and this change is so slowly that we are considering that the process is almost considered to be in state of equilibrium. Just like the laws of thermodynamics, we are giving some example of the zeroth law of thermodynamics, where two bodies are in thermal equilibrium with a third body, so they are considered to be in thermal equilibrium with each other. Here we have an example of iron and copper that are at different temperature with each other. The iron temperature is 150 degrees C and the copper temperature is 20 degrees C, and both the objects are brought in thermal contact with each other. So what happened? The heat flow from the body of higher temperature toward the body at lower temperature, and this flow of heat continue until both the bodies achieve the same temperature. So here we are looking at the final configuration that the iron has a temperature of 60 degrees C, and similarly the copper has also the temperature of 60 degrees C. So in this case we can see that the bodies are brought in thermal equilibrium to each other. So we are revising some of the concept that is regarding the statistical mechanics, as we already discussed in the beginning of the lecture that this is not actually the part of our course, but for the basic understanding and for developing the microscopic approach of any particular system, we also included this to be as a general discussion regarding the statistical mechanics. So statistical mechanics, we study the object or any particular processes microscopically. So equilibrium statistical mechanics is also referred as a statistical thermodynamics, and this is actually the branch of science pertains to systems in thermodynamic equilibrium, and thermodynamic stress is also is known as the macrostate of a systems and it can be described by macroscopic parameters just like pressure, temperature, volume, and some other parameters. So the statistical mechanics is described by the quantum state of any particular systems, that is actually called as the microstate of any particular system, and it requires a large number of variables to describe. So for this we need to have some large number of particles. If we have large number of particles, it requires a large number of variables to describe the microstate. Just like if we have J, if we have J, so we have that particular system as the number of particles is large, so it requires large number of variables to describe the microstate of any particular system. So in special cases wherein the particles do not interact with each other, like the molecules in an ideal monoatomic gas, so what happen, it need to specify the quantum state available to each particle. So classically, microstates can be described by giving the position and velocity of all molecules. So the microstate is experimentally accessible, or it could be observable, while the microstate are not, because it's very small. So some of the other postulates that are describing the statistical mechanics is actually the heart of statistical mechanics as the concept of ensemble, or the couple of, and some postulate as well. Ensemble is actually the assembly of particle. So maybe in the classic, in thermodynamics, in statistical mechanics, we need to know the nature of particles, and to describe the nature of this particle, some postulate are developed, and the most important postulate is the postulate of probability, in which it is mentioned that if there is some possibility, or there are some chances for any particular events, so all the chances are equally probable. So in macroscopic description of any particular system, we carry some average values. So just like if we consider the pressure, in case of pressure, the pressure could be obtained by the momentum transfer per unit area per unit time by the molecules in any particular gas, but instead of time averaging, we typically use the concept of ensemble and postulate in case of statistical mechanics. So the measured time average of macroscopic property in a system is equal to the average value of the property in ensemble. So all ensemble is actually the assembly of particles. So if we consider an example, that is a collection of infinite number of isolated systems which are in the same macrostate as the systems under consideration. So another way of looking at this particular system is the infinite system, and that is why we have different sort of particles that are involved in that, and we want to measure their property and then finally average it to get the final values of that. We have statistical thermodynamics as well, where a system typically consists of large number of entities, just like atoms, molecules, and ions, and sometimes it could be referred as a particle. So this implies that the system is associated with large degree of freedom, microscopic. So the concept of degree of freedom is also very important in case of statistical mechanics. Degree of freedom is basically represented by DOF, and it implies that there are large number of microstates corresponding to a single microstate. That is actually called as a degeneracy of any particular state. So the macrostate, unlike the microstates, can be described with a few variables, just like we have some theorem that is used to describe any particular systems, and that is used for that. And the general thing is we need to sum up the values, just like we have a simple equation for the internal energy of any particular system. The U is equal to summation of Pi epsilon I, where Pi is the probability of microstate, I is the name of any particular particle, a particular microstate, Ei is the energy of ith microstate, and summation I is the summation or the ith microstate. So this actually simplifies the matter, as now we need to the probability of finding of any particular microstates. So we have some depending on the configuration, we have some particular type of ensemble. The nature of particle are different from each other, and we have general description for that, just like we have canonical ensemble, microcanonical ensemble, grand canonical ensemble, and just like some other ensemble, but that are considered to any particular and special configuration for which is name is given. So we have probability theory for any particular microstate, and the probability of a microstate is a function of its energy, can be computed using the Boltzmann distribution, and the Boltzmann distribution is equal to e⁻ epsilon I divided by kt, and the whole divided by epsilon I e⁻ ei divided by kt. So this is actually the this can be combined with the Gibbs entropy equation to compute the entropy of any particular system, and we can calculate the entropy, which is equal to S is equal to minus K summation pi natural log and pi. So from that we can calculate the entropy of a system. We have the general equation from thermodynamics regarding the entropy of a system, that is S is equal to K natural log sigma. So from that we can get the entropy of any particular systems. So some different notation is used for the Boltzmann equation or the Boltzmann-Planck equation, just like we often write omega instead of the capital omega, that is S is equal to K log capital omega, or we can also write as S is equal to K natural log of omega, the same, that is actually the small omega. So omega is in capital, this is actually the capital form of omega, and this is small lower form of omega, is the number of microstates that is available to any particular systems. So currently we are not asking, we don't need to know that all these microstates will actually be explored by the system or not, but we are basically interested in all possible microstates. So this is any particular configuration of the systems where we can represent by the small omega or capital omega. That is actually the number of microstates available to any particular system. So in general we have Sm is equal to K natural log of omega m. So this is actually the systems which have multiple macrostates, and the entropy of the mth macrostate is computed using the number of microstate corresponding to any particular system. So this is what we call as a total entropy of the system, could be and it could be represented by Sm, that is equal to K natural log of omega m. So we have another thing that is important to us, that is actually S, capital S, and it is equal to K into natural log of omega order plus disorder systems. So that is actually almost equal to K natural log of omega disorder system, and this basically describes the number of microstates including for both disorder and order systems. So actually the number of disorder macrostate is greater than the number of order microstates, so that is why the logarithm of the number of microstates can be approximated by the logarithm of the number of disorder microscope. In that particular case we have the last term of this lecture, that is actually the residual and entropy of this particular system, and the residual entropy, that is actually defined as it is actually the classically description of entropy, where the classical defined entropy, that is the macroscopic interpretation, is 0 at 0 Kelvin, and that is actually also called as a third law of thermodynamics, that the entropy of any macroscopic system is 0 at 0 Kelvin or constant at 0 Kelvin. So in any statistical picture of the entropy of that particular systems, there could exist a multiplicity of microstates even at 0 Kelvin. So this is actually the so in statistical it is in the statistical picture of entropy, there could exist a multiplicity of microstates even at 0 Kelvin. So this degeneracy or multiplicity of states give rise to a configurational entropy at 0 Kelvin. So if you consider an example of argon crystal, at 0 Kelvin versus the carbon monoxide crystal at 0 Kelvin would happen. Unlike the argon crystal, the linear CO carbon monoxide molecules has a two orientation, that is orientation up and orientation down. In in a crystal at 0 Kelvin, if the up and down states are randomly positioned on the lattice, so this will give rise to a configurational entropy, and this leads to the this will lead to the residual entropy of carbon monoxide at room temperature. So this is something assuming that the order and disorder states have the same energy. So this is particular systems or configuration of that any particular system. So this is something about the statistical mechanics in general.